Okay. So, maybe let's get started. I am super excited to introduce Geoff Pleiss. Geoff is an assistant professor in the stats department here at UBC. He's our first member of the HC cluster from stats.
But no longer only.
No longer only. There's another one. Oh yeah, well in CS, yeah. Oh yeah, CS. There's another one in stat. So yeah, Geoff did his postdoc at Columbia with John Cunningham. Did a PhD at Cornell with Killian Weinberger. Geoff does tons of really interesting work at the intersection of modern machine learning and statistics. Does work on neural network uncertainty quantification and Bayesian optimization, Gaussian processes, ensemble methods. The list kind of goes on. Geoff is also known for some really solid software work. So if you haven't heard of GPyTorch, Geoff is one of the co-creators of that with Jake Gardner. And well, with that, I think Geoff is going to tell us today about ensembles in the age of overparameterization. So, thanks, Trevor.
Yeah, thanks, all. I'm really excited to be chatting today here about ensemble methods. This started off as, or really where this came out of was, this was me implementing a baseline for a project on uncertainty quantification that I was doing during my postdoc 3 years ago. And it was just supposed to be like, 2 days, like here I'm implementing some sort of ensemble baseline. I'm just going to compare that to the method that I have, and then I'm going to be done. And then what ended up happening was I ended up killing the project that I was working on, but it started this then 3-year-long like obsession and deep dive into trying to understand ensemble methods, and in particular thinking about what ensembles mean nowadays when the models that we have are no longer small decision trees, but these potentially very large neural networks. And so I guess to motivate this idea a little bit, I like to go back to what I've been emphasizing in Stat 406 as the most important concept in all of machine learning, which is the bias variance trade-off. And this is, of course, the bias variance trade-off is one of the best ways that we could think about understanding the generalization properties of any single model in statistics or machine learning. So largely speaking, what I have here on the x-axis is this notion of capacity. So basically, if we think if we have some sort of model, how good is this model at actually fitting data that we have available to it, or rather, like how much capacity is there to fit, any given training data set. And what we learn about in any introductory, statistics or machine learning course is that there is sort of this Goldilocks zone that we'd like to have for models, where we don't want them to be too small, not enough capacity. We don't want them to be too large, to be too complicated. We want them to be just right. And that's what leads to the best generalization error. We see this middle line here for any single model on this plot over here. And so if our model is like too small, it's too simple, it's not complex enough, we are in this regime where we have a lot of bias, where no matter what training data set we gave to this model, we're going to end up with something that's just not really able to have. It doesn't have the complexity to fit what we're seeing in the data. On the other hand, if we make our model too complex, we're in this high variance zone where now we have the ability to fit any training data set that we give it, but now the type of or the actual predictor that we ultimately end up with really depends a lot on the particular training data set that we had. The way that I learned about ensembling, really came to understand about ensembling, is really this way to resolve what happens if we end up either of these two extremes. If sort of we have a single model that ends up in either this high bias or high variance regime. So if we have a set like a model class that is high bias, so for example, we have these like decision stubs that are just like a decision tree that's just making a few splits here or there. We have a way of combining multiple of these models together in a way to reduce the overall bias of the predictions that we're making. And this is a method known as boosting, which is a way of, again, combining a lot of very high bias weak learners into something that is ultimately a strong learner. Conversely, if we're over on the other extreme, ensemble can also help us in this regime as well. So if we have maybe much larger, more complicated decision trees, we have a method of, through ensembling, reducing the variance of these base classifiers through something like bagging or random forests. And so ensembling really is this way of, if we think about where we're at on this bias variance curve, it's a way of resolving either high bias or high variance, or both. We have some sort of fun combination of the two of these. And this, I think, is a picture that, for many of us who study machine learning, it's a picture that we get in our mind through like our own study, through classes we've taken, through research we've done. This is sort of how we envision ensembles, I would say. What we now know in the last 5 years is that this bias variance curve that we have come to know and love is actually an incomplete picture as to what's actually happening in the real world. I think that there was this understanding that, you know, if we just kept increasing capacity more and more and more, all that we're doing is we're just ultimately like increasing our variance more and more and more. We used to think that this curve would just kind of go off, you know, shoot up into the moon. What we found, though, recently in the last, I think, 5 years, that this phenomenon of double descent was first kind of discovered and introduced, which was that there's actually an inflection point that occurs on this bias variance graph, where as soon as we start to increase capacity beyond the point, what is often referred to as the interpolation regime, the regime where we can perfectly memorize a training data set, if we continue to further increase capacity, what we notice is that actually our generalization error continues to decrease with additional capacity. So we're seeing that bias remains relatively constant, or potentially, you know, doesn't really change too much, and our variance is actually decreasing now as we increase capacity. And we now, many of our modern models that we use end up in this overparameterized regime, neural networks, of course, being the canonical example. And the question that I have is, what does it mean now to form ensembles in this regime over here? Ensembling is this way that we can resolve high bias or high variance in this sort of classic underparameterized regime. What does it now mean if we're ensembling way up over here in this overparameterized regime? Yeah?
What kind of data to gather? What's your
I'm talking about any kind of data. So this is going to be agnostic to data. Like I'm going to have some experiments that are just on sort of like, you know, small regression data sets. I'm going to have experiments where we're dealing with like large image classification. So not specific to any kind of data.
So does the double descent only occur with deep networks, or just
it does not? It does not occur with deep networks, and so there's a reason that this is this talk is called Ensembles in the Age of Overparameterization and not Ensembles in the Age of Deep Learning, because what I hope to convince you of is that this is not necessarily some phenomenon that is just specific to neural networks, but this is going to be something that is actually more broadly applicable to just like high dimensional statistics.
And when you say ensemble, you mean multiple models that are trained on different data sets?
No, I'm going to give a precise definition of what I'm talking about in a little bit. It is multiple models, all of which are going to be slightly different, but they don't necessarily have to be trained on different data sets. And actually what we're going to see is that in the case of like the sort of the ensembling recipe that's often used with deep learning, it's usually the same data set. And so I guess, does it even make sense to consider, well, I guess, before I get to that, kind of the take-home message that I have for this talk is that classic intuitions that we have about ensembles that we've gotten through things like boosted, or like gradient boosting, for things like random forest, those are not going to apply when we're now thinking about ensembles of overparameterized models. And in many cases, those intuitions that we have can actually be backwards. They can lead us completely astray. Why does it make sense to ensemble overparameterized models in the first place? Maybe by the end of this talk, I will convince you that maybe it doesn't actually make that much sense, but people do it a lot in practice, right? You know, we could have, if we have a very large neural network that, you know, is able to make good predictions on a particular data set of interest, 10 neural networks might be able to make even better predictions, and that happens a lot. And yes, that might be more computationally expensive because now rather than choosing one very large neural network to make predictions, we're now using 10. But this is something that people often do in practice, especially when computational resources aren't necessarily a huge limitation. It does ultimately lead to increases in accuracy, which is, you know, of course, what's driving a lot of, why we use specific methods in machine learning. But also there is a lot of evidence and a lot of belief that when we have multiple neural networks that we're combining in a way to make predictions, this could be a way to increase robustness and to also obtain uncertainty estimates. If we have neural networks that are all making slightly different predictions, this in some sense should give us a notion of uncertainty if the neural networks are all making different predictions versus if they're all making the same prediction. I have these thinking cases by those last 2 points because I hope to draw some, or make you a little bit skeptical of those claims towards the end of the talk. But this is something that is being done a lot in practice, especially for applications that are safety critical and also for applications where people are trying to use neural networks as part of some larger decision making. So ensembling these big overparameterized neural networks is something that people are doing in practice. And in this talk, I want to try to better understand what is actually going on when we are ensembling these large neural networks. How does it really differ from when we have more traditional ensembles of smaller models like decision trees? I'm going to offer some both empirical and theoretical evidence towards the differences between sort of ensembling of these two regimes. And then I'll kind of end with some practical considerations or some implications from these differences that will hopefully answer this question of if ensembling is actually useful or meaningful or doing something that's different in this overparameterized regime. I want to start off with some empirical evidence, and I've got to kind of tell this story backwards from the way that I encountered it through my research. So I'm going to talk about some more recent research first, and then kind of work backwards to some of the more original studies that I did on this. So now to rigorously define, like, what do I mean by an ensemble in this case, and specifically, what do I mean when I'm thinking about ensembles in this overparameterized regime? So there's a term that appears a lot in the neural net literature called a deep ensemble. A deep ensemble, if you come across that term, basically just refers to an ensemble of neural networks. We like to throw the word deep in front of everything that has neural network associated with it. That's really all that there is to it. What is perhaps interesting about the recipe for these deep ensembles or these ensembles of neural networks is that there's not really anything that's super different in the training procedure of the multiple neural networks that I'm considering to ensemble together. So,
sorry, but you said this can apply not just to neural networks, SVM, whatever you want.
The results that I have are going to be applicable to models that are over-parameterized more generally. So yeah, it should be applicable to, I'm going to show some results and introduce some theoretical results with over-parameterized random feature regression. But I think that kind of where this is most broadly applicable is going to be to things like neural network ensembles.
So SVM is RBF kernel, and you can over-parameterize as much as you want.
Yeah.
Does that apply to it?
Yeah, I mean, yes and no. I think that these results will apply to it, but I think with some caveats, just because like the recipes that we're going to be using are not necessarily something that would immediately transfer to SVMs. So yeah, in particular, the recipe here is, which I think is quite interesting if we think about like sort of traditional ensembling methods, is that the neural networks that I'm going to be combining ultimately in this ensemble are all going to feature the same architecture. So if I'm say using like a ResNet32, like a very standard image classification architecture, I'm going to have multiple copies of that architecture. They're all going to be trained using the same training procedure. They're all going to be using the same data. So I'm not going to do any sort of bagging or any sort of data splitting when I'm training these different models. And they're going to be independently trained on the same exact objective. Like I'm not doing any boosting here. So what is actually going to be different about these different models? Not much. Really, all that's going to be different is different parameter initializations and different mini-batch ordering. So different sources of randomness that go into the actual training procedure of this model. But because neural networks are, the optimization problems for neural networks is this big non-convex optimization problem, what that's going to lead to is the parameters that I end up with in these neural networks being different just due to this inherent randomness in the ordering and the initialization. And that is going to lead to a set of predictors that is making different predictions.
I don't want to drift in myself. Can we use fully connected networks?
Yes, this applies to that.
Okay, sir.
And what we do is once we get these networks and we have all of them, we're going to just form an arithmetic average of their predictions. Here I'm going to often use regression based terminology and examples here, but all of these results also apply to classification. I think the math is just a little bit nicer when we think about arithmetic averaging and regression and all of that. And one of the nice things about this recipe is it's guaranteed to work to some degree. In the sense that if I think about, again, using sort of squared error as a notion of loss or risk here, basically as a consequence of Jensen's inequality, it's going to be provably true that the risk that I have for this ensemble is guaranteed to be less than the risk that I have for any one single model. And of course, because we're dealing with squared loss here, if we're thinking about things in a regression context, the difference between the risk that I have for any component model and the risk of the ensemble is going to, the difference between those two is basically going to be given by the variance of the predictions that we're getting from any one single model. There's this n-1/m, which is basically just due to the fact that when I'm forming an ensemble, I'm only considering n possible different models. We can ignore that constant for all intents and purposes, but there's this nice formula that just falls out of, again, just by using the squared loss that relates sort of the basically the error that I expect on any one individual model, the error I expect from my ensemble, and the variance in the predictions that I have from these ensemble members. And one thing that I noticed when I was starting to look at ensemble methods, and especially like in the context of deep learning, is staring at this decomposition a little bit. There was something that really caught my eye, which was when ensembles are independently trained, I could think about independent training of models as equivalent to training all of these models simultaneously, but using a loss function where I'm trying to now minimize the error of the average error of these different models over here. And this will work out if you think about the computation graph that is formed through, say, like independent training, and if I am now trying to minimize each of these losses independently, that would be exactly the same as if I tried to minimize the average of the losses of each of these individual networks. So when I'm thinking about training an ensemble in practice, I can think about the training loss that I have is now equal to essentially like what would be the empirical risk of my ensemble plus the variance amongst these ensemble members. And this really caught me by surprise as I was thinking about this a little bit more, because this seems a little bit backwards. The loss that I'm trying to optimize is the thing that I actually care about. And now this term where essentially I'm penalizing there being variance amongst these different models. And this felt backwards because in some sense, the reason that an ensemble method actually works is because we are making diverse predictions. And yet, thinking about the loss and the training procedure that we have for training independent ensemble members, it actually seems as if, like, when we write it this way, we're penalizing having variance amongst these different models. And this was something that I found really strange. So we decided to run a very simple experiment, which was, what would happen if we tried to train ensembles in a more joint-friendly way? So like one where we're penalizing variance a little bit less. It's just under. So we instead tried to train ensembles where we were now not independently training them, but jointly training them, where rather than having this formulation where variance kind of falls out of this natural penalization term, we're instead going to change how much we encourage or discourage variance amongst the different members that we have in this ensemble of neural networks. So we introduce this hyperparameter lambda. When lambda is equal to 0, we basically have standard ensemble training where all the models are trained independently. When lambda is less than 0, we are now downweighting this variance term, so we're encouraging diversity over standard ensemble training. And when lambda is greater than 0, now we're upweighting this variance penalty, so we're discouraging diversity amongst these models. And I had an idea of what I thought the results were going to look like. And in practice, they ended up being totally backwards from what I expected. So here, what I'm plotting is, this is the results for an ensemble of image classifiers. These are resonant 18 models, so like a pretty small neural network by today's standards, but one that still is commonly used. These are all trained on the CFAR10 dataset, so a standard image classification dataset. This gray bar over here shows the accuracy of one single model, or in the ensemble, where the gray region represents a confidence region. This blue line up here, that represents a standard ensemble where I'm doing independent training. And now I'm plotting these x's correspond to ensembles with different amounts of this predictive diversity penalty, where again, I'm encouraging diversity when lambda is less than 0, and I'm discouraging diversity amongst these ensemble members when lambda is greater than 0. What we see is that when we set lambda to be less than 0, we see that performance becomes worse. So the more we encourage diversity by decreasing this variance penalty, we are ending with ensembles that were worse. And surprisingly, when we discourage diversity amongst these models, we basically were, in some sense, trying to get all these models to produce exactly the same prediction. It ended up being mostly a no-op, and maybe even in some scenarios, we found that it could actually benefit the ensembles. We ended up with a better ensemble when we were discouraged, when we were trying to basically get them all to make exactly the same prediction. Just to prove that we're not totally crazy here, that there wasn't just something that I think when seeing results like this, especially with neural networks, one should always be skeptical and thinking, well, clearly they did something wrong. Like, they obviously set the beta parameter in Adam to be 0.095 instead of 0.099, like total amateurs. Like there's always like these weird like things that you could when training neural networks that could easily cause weird instabilities that could lead to these results over here. So just to prove that we're not totally crazy here. Again, if we think about the performance of an ensemble sort of consisting of these two components, the risk of our component models that we're using, so the average error of any one single model in isolation, and then the variance amongst them, these are two terms that we have that affect ultimately the performance of an ensemble. So we have like two different recipes for creating ensembles that perform really well. We could either have component models that are all really good, but basically producing the same prediction, or we could have component models that are all kind of bad in isolation, but they have a lot of variance amongst them, and so we're averaging out all the errors amongst them. So we can plot these two terms here on this plot over here, where the diagonal lines here are then going to correspond to level sets of our ensemble risk. And what we ultimately found, I'm not showing the exact plot here that we used in practice, but this is it's a cartoon illustration of what we found, is that when we have standard ensemble training, we basically end up with models that are all really good in isolation, that are all pretty much the same. And when we set that lambda hyperparameter to be less than 0, so when we were encouraging diversity, we were ultimately ending up with models that had more predictive variance amongst them. But in doing so, we so much harmed each individual model in isolation that the net effect was to yield a worse ensemble. The cost of increasing the variance among these models was so great, we were hurting each of the individual models so much that the increased variance that we got was basically negated by the fact that all of our models were so much worse in isolation.
Could you repeat how you produce these level sets? So it's some analytical computation or something?
Yeah, this is perfectly analytical just because here, so it's we have variance on the x-axis, the average single model performance on the y-axis, and the ensemble risk is basically just subtracting those two terms from each other. So those level sets are and when we'll see this plot later, and then we basically just kind of like we could look at the component models in our ensemble, we could look at the performance of our ensembles in isolation, and just naturally do these quantities. So why would this actually be the case? Why would encouraging diversity amongst models actually be harmful? And why could discouraging diversity actually potentially be beneficial? This is a very hand-wavy explanation, but this is the best intuitive explanation I have. Is, again, we are no longer in this classical bias variance regime that we have come to know and love through most of our years of studying machine learning over here. That would be true if we had these very small neural networks, but when we're using these very large neural networks, we're way up in this overparameterized regime. And being in this overparameterized regime, the consensus that the neural network community has come to some degree is that we could think about overparameterization and in fact like making models increasingly larger is there's some sort of variance reduction that is happening as we are making these models larger. And this seems to be the secret sauce of neural networks. Is as we make them larger, we are somehow reducing the variance of these models. And so increasing capacity results in variance reduction. Ensembling is also this tool that results in variance reduction as well, right? Because or when we are combining all of these models together, we are essentially like averaging out whatever variance is there in each of these or whatever these differences are amongst these individual models. And so if we're now trying to encourage more diversity amongst these models, we're trying to increase the predictive variance amongst them. In some sense, we're counteracting the secret sauce that makes neural networks work. We're counteracting this variance reduction that we get through overparameterization. And that wouldn't happen again if we were over, here on the underparameterized regime area, because there, as we are, because there, what we are trying to do, we'd be trying to essentially fight the increased variance that we get from increased capacity, where ensembling and encouraging more diversity could potentially be beneficial. Over here, we are essentially, if we are trying to increase the predictive diversity amongst models, we are then fighting this sort of secret sauce that seems to be making neural networks work in this overparameterized regime. It's a very hand-wavy explanation, but that's the best intuitive idea that I have. And just to show that this idea of whether or not we're over or under parameterized really comes into play, we repeated the exact same experiment that we had here with the larger neural networks with these really small neural networks, these 8-layer residual networks, which are not, they're well, not only small by today's standards, but they would be small by standards from a decade ago. They're incapable of fully memorizing a training data set like CFAR. So these are very much models that we would consider to be under-parameterized, falling again towards our classic intuitions. And there what we found is when we repeated this experiment, we saw what aligned more with our intuitions, that encouraging variance amongst these models in our ensembles, which trying to create more diverse predictors, was beneficial. And again, creating models that were more similar to one another was harmful. So where we lie on this under-parameterized versus over-parameterized spectrum really seems to be making a difference for kind of like what goes into making these ensembles work really well.
Are you trying to play with the training data size? Like instead of 60,000, you have make it 6,000.
I think so. We didn't run that experiment exactly. What I would imagine would be the case is that that plays a similar effect to thinking about decreasing or increasing the size of the neural network. So when I consider like an over-parameterized neural network, that basically corresponds to something that is capable of memorizing training data. So if I were to keep a small neural network, but I were to train that on a smaller data set, then now perhaps that neural network would be capable of memorizing this much smaller data set, and so it would behave more like an over-parameterized model. That would be my hypothesis, but again, it's not confirmed necessarily by experiments. So another thing that we considered is, so I've now talked about basically introducing a hyperparameter that would increase or decrease or encourage or discourage predictive diversity amongst these neural networks. And a fair criticism that we saw when we first discussed this work with some collaborators is that there are ways of obtaining predictive diversity amongst different models in ways that aren't necessarily going to incur a trade-off. So there are what we call these free sources of predictive diversity that are out there. For example, if we modified this training recipe that we had where we were ensembling together, essentially like the same neural network architecture, just different, all that we were changing was going to be the initialization and random ordering of things. What if instead we used multiple different types of neural network architectures? Again, we can think also about using slightly different training procedures for each of these individual models. But like doing something so that we were perhaps by using, say, like different training procedures, different model architectures, we could incur a little bit of extra predictive diversity that wouldn't necessarily come at the cost of the performance of any one individual model. And it is true. There are basically ways of, I could consider, say, 3 different neural network architectures, 3 different training procedures, all of which result in models that have roughly the same performance, but are all going to produce slightly different predictors. So I can basically keep the average component model error the same and just push myself a little bit further over here on the x-axis, increasing the predictive diversity, have a little bit more, which is going to move me down these level sets. That is totally valid. There are going to be these ways where we can encourage more predictive diversity amongst our models in a way that isn't harming our individual component models. We found that in practice, there was this opportunity cost of doing that. And that if ultimately at the end of the day, what I want is I want a recipe that is just going to produce me a better predictor, there's a much better strategy than trying to explore these notions of predictive diversity and ones that might be free. What I should do is I should just train much bigger neural networks and I should ensemble them together. And when I do that, I'm basically going to much more dramatically reduce the amount of predictive diversity that I have amongst these models, because what we find is that these larger neural networks on this bias variance trade-off, this sort of double descent portion of the bias variance trade-off that we're in, these larger neural networks are going to be much less diverse. But ultimately, when we average them together, we are going to end up with a predictor that is much better than what we could have obtained by neural networks that had more predictive diversity amongst them. So putting that into practice, what I'm plotting here is we trained multiple ensembles on both the CFAR10 image classification dataset and the ImageNet classification dataset. We didn't train all of these models. We asked a lot of collaborators for whatever models they had lying around. We just averaged a bunch of them together, forming these different homogeneous and heterogeneous ensembles. Again, what I'm showing over here is these dashed lines correspond to level sets of ensemble performance. So any two ensembles that lie on the same line get the same, those ensembles get the same error on a given test set. And what we notice is on these plots, the best ensembles, so the ones that obtain the lowest level sets, were almost always in this kind of bottom left quadrant over here, which again is going to correspond to ensembles where all of our individual models, we have really good performing individual models that aren't necessarily super diverse. So if we continue trends that seem to be happening in the deep learning world, ultimately what we're ending up with is a lot of very, very powerful models, all of which are not too diverse, all of which are kind of basically producing roughly the same predictions. And any way to try to increase predictive diversity amongst them is only ultimately going to lead to worse models, even if we try to ensemble them together. And this, I think, was very counter to a lot of our intuitions that we had, where if we think about really, really large models from kind of a classic bias variance perspective, we would think there's a lot of potential models in this large space. And so that if we train multiple neural networks that are all very large and all of this high capacity, they should all be producing very, very different predictions. And averaging them together, we should be able to get a very meaningful notion of variance amongst these models. Averaging them all together should yield something even better. And ultimately, what we're finding is, no, that's not the case. In this overparameterized regime, all these models seem to be kind of collapsing onto one another, and trying to think about ways of encouraging diversity amongst them only seems to be hurting ultimately the performance that we would be expecting out of an ensemble.
Here we are talking about the boss, but what about the generalization?
I mean, this is the generalization. So this is the test loss here. I'm going to move on to the next part of the talk. So I'm going to just pause here for any questions.
In the previous slide for the right image, I can see that the yellow line is kind of like going down below the homogeneous. What was kind of your understanding of that part?
Are you talking about the distribution?
Yes.
Yeah. That's a good question. I will defer that to the next set of slides where I'll investigate that in a little more detail.
Just quickly asking about dropout. So where does that fit into the picture here?
So like you're thinking about like ensembles that are formed through dropout. So these are sort of these like implicit ensembles as people have been describing them. We found that those ended up really being kind of actually, if there's like some sort of Pareto frontier of ensembles here, we found that those were actually like flying quite far off the Pareto frontier, because you weren't necessarily, like, you would get a lot more variance amongst your models if you were to train independent models rather than, training a single model and, using dropout. So they kind of ended up, being suboptimal in a lot of ways. I mean, the advantage there is you only have to train a single model versus training multiple models, but then at test time, you're still having to forward your predictions through the, it's the same cost of test time.
Did you try anything outside the image data?
Not in these experiments, but in what I'm about to show next week. So, as I said in the beginning of this talk, even though so far I've only talked about neural networks, and again, neural networks trained on image data, I titled this talk as about overparameterized ensembles more generally. And again, thinking about taking any claims about neural networks with a grain of salt, showing that this is not necessarily an issue that we could get around if we had used weight normalization instead of batch normalization, or if we had used, exponential learning rate scheduler or whatever, any of these sort of like things that can affect performance in neural networks in particular. This is actually a very robust result that I think applies more generally to overparameterized models and, again, lots of different types of data. So, a model that we considered and we thought about was this model known as like random feature regression. which is a model that people are often using now, especially in the neural network theory literature, as a theoretically tractable approximation to neural networks. The way that you can consider these models is that I can imagine I have a 2-layer neural network where the weights in the first layer of the neural network are randomly initialized and fixed. And so all the only weights that are trainable are these last layers, are the weights in this last layer, which are combined to make my output. If you squint at this and think about it for a little bit, you will see that this is in fact just linear regression, because with a random basis expansion that I'm using over here, because these weights are fixed. All I'm doing is I'm now basically training these last weights to produce a linear response with respect to whatever I get out of these random features that I'm using. And so this is like I said, a model that is now very common in the neural network theory literature, because we know, at least, we don't necessarily know how to perfectly analyze linear regression, but we have a lot better tools towards analyzing linear regression than we do for analyzing neural networks. And they actually happen to be a very good approximation of neural networks, even in practice, depending on the exact parameters that you're using. So here, one of the nice things about analyzing linear regression is that linear regression and the optimization problem associated with linear regression is convex. There's not going to be any sort of feature learning or any architecture-specific things or any optimization-specific things that happen under the hood. Like, I can in fact produce the optimal, or the solution of whatever optimization problem I have with linear regression in closed form. And so if we're able to see sort of similar trends occur that I showed with neural networks in the case of this random feature regression, then we have the sense that the results that we're seeing are probably more robust, are robust to any specific neural network choices that we were to make. What I'm showing over here now on this plot is, again, this we created ensembles of random feature regressors, again trying to mimic the style of what we had for deep neural networks, where we keep the training set fixed, we keep the training procedure fixed. The only source of randomness now is in the random features that we're using, which again sort of corresponds to, in a lot of these deep ensembles, the only thing that we keep random is initialization and all of that. And what we found is then we're seeing sort of similar trends with ensembles of random feature models. Here on the left over here, the dots and the size of the dots correspond to the size of the random feature regressors that I'm using. And again, it's going to be the same decomposition of the ensemble performance into the average single component model performance and the predictive diversity. Level sets again correspond to ensemble performance. What we notice is that as we increase the size of the random feature regressors that we're ensembling, we see this kind of initial drop in performance where our models are getting better. They're basically saying just about that they have the same amount of predictive diversity amongst them. And then we're seeing that, well, we might be kind of flatlining, we might be getting a little better. It's hard to say in terms of the ensemble, but our variance is very dramatically spiking as we start to increase the size even more, as our average component model risk is also getting worse. And then there's this inflection point up here at the top right, after which point, now as we further increase the size of the predictors that, or the random feature models that we're using, we now see, do continue to see an increase in performance. But what's happening is we are seeing sort of exactly the same trend that we saw in the previous slide, where our individual component models are getting much better, but they're also getting more common. They're also getting more similar. We're also seeing a decrease in diversity. So that inflection point that exactly corresponds to the transition between the underparameterized and the overparameterized regime. In a paper that was just put up on arXiv yesterday, actually, we can characterize this trade-off exactly. I think probably what makes the most sense is I'll put up this very informal description of the theorem that we prove. But when I'm thinking about ensembles, especially in this random feature regime over here, right? Like the more models I add to this ensemble, eventually I'm going to completely destroy this variance term that I have on this bias variance decomposition over here. Because if I were to have infinitely many models where each of those models basically contains a random set of features. If I include many of them, I basically am going to average away whatever randomness was present in those individual features. Of course, I'm going to use a finite ensemble in practice. There's still going to be a little bit of variance, but this variance term is basically going to be proportional to about 1 over m, where m is the number of ensemble members that I have. So when I want to think about ensemble performance, the thing I should really be paying attention to here is the bias of any one individual model, because ultimately that's going to be equal to the performance of an infinite ensemble. And what we characterized in this recent paper that was just released on arXiv is that when we are in the underparameterized regime, if we're considering random feature regressors, the bias of any one random feature regressor, or equivalently the risk of our ensemble, is going to, in the limit of having infinitely many ensemble members, is going to correspond to the risk that we would get from a kernel ridge regressor, where the kernel that we are going to be using is exactly equal to the expectation, or the second moment of our random features, with where is the second moment with respect to the randomness in the random features themselves. In the overparameterized regime, we also end up with the bias of a random feature regressor also being the same as kernel regression, but it is kernel ridgeless regression. So in the underparameterized regime, we basically this ensemble of infinitely many models that we have is equivalent now to a large but regularized model. And the amount of equivalent regularization that we have is going to be inversely proportional to this, the size of these random feature regressors that we have. But now once we enter this overparameterized regime, what we find is that now our ensemble is going to be equal to this ridgeless regressor, and that's going to be regardless of the size of the model that we have in this ensemble.
This example is SVA with linear kernel because it's maximizing margin.
This is for regression, so not for classification here. I mean, we did not make that comparison, but I don't think that this was trying to make a comparison. This was trying to understand the behavior of random feature of this particular class of random feature.
So you might just increase the margin. More models, when others say increase the margin with respect to
as in adding more features to the random feature regressors, or as in adding more ensemble members?
If you increase the number of ensemble, you basically increase the margin.
I would say let's talk more. In the interest of time, I want to move on if I can take this question offline. And so what does this mean now in terms of this this plot that I'm showing here? Basically what's happening now is in this overparameterized regime, what we're finding is that, or sorry, in this underparameterized regime, what we find is the reason that that in this regime where I'm seeing this increased variance, but I'm still seeing overall a better ensemble, is because as I'm increasing the size of, as I'm making my models wider and wider, what I'm actually seeing is I'm actually seeing a change in my bias. I'm seeing an effect of less regularization overall, which may be beneficial for certain data sets. And so that is sort of seen to be potentially a good thing. Once I now end up in this overparameterized regime, though, basically, if I were to have an infinitely large ensemble, I would basically see all of these different ensemble members lying exactly on the same flat line. My bias stays constant. The only reason now that I'm seeing improvement in performance as I am decreasing as I'm increasing the width of my individual models is in part because I'm using a finite ensemble size. And so now it's basically going to depend on what is the variance of any one individual model in my ensemble, which is going to improve as I increase the width of these models. And so just to show that this theorem actually does hold, what I'm showing here is a very simple one-dimensional toy example where we are training an ensemble of random feature regressors on this very simple data set over here. These are all overparameterized random feature regressors. So I think that I think there was like 100 random features in each of these experiments. The dotted line, the dotted pink line shows the corresponding kernel ridgeless regressor. So this would, one way of thinking about this is the equivalent of if I had one single random feature regressor that was infinitely wide. And what we are indeed, in fact, finding that this ensemble of random feature regressors, the average of each of these random feature regressors, which again corresponds to the ensemble prediction, exactly corresponds with the kernel model that we're using in practice. So going to quickly the implications of what that means in the case of now deep neural networks is when we're in the underparameterized regime, there is a distinct difference between an ensemble and versus any one single model. In the case of random feature regressors, I could be averaging a bunch of underparameterized, unregularized random feature regressors, and ultimately what I end up with now is a regularized model. So there is something like ensembling is doing something in the underparameterized regime. I'm getting something that I'm getting something out of ensembling that wasn't necessarily corresponding with my input. In the overparameterized regime, that kind of goes away a little bit. When I'm ensembling, if I were ensembling many models together that are all unregularized, ultimately I end up with something that's unregularized out of it. And in fact, if I ensemble infinitely many finite width models together, I end up with something that would be equivalent to a single model of infinite width as well. Which sort of begs the question then, in this overparameterized regime, which is better? If I now no longer thinking about infinitely wide models, but if I have, say, like some finite computational budget, I could instead choose to train many smaller but still overparameterized models versus one very large single model with that say is m times as wide as the ensemble members that I was considering. And of course, as that budget goes to infinity, and at least in the case of random feature regression, what we're finding is that there is no difference. In practice, we also noticed that that was true even with finite budgets, and not only with random feature regressors, but also going back to neural networks. There wasn't necessarily much of a difference between one single large model versus many slightly smaller but still overparameterized models. What I'm plotting here now is a point-wise comparison between, again, like on the CPAR-10 image classification data set. What I'm showing on the x-axis is predictions that were made using an ensemble of, I think, resonant 18s. On the y-axis, I'm showing for those same data points, the corresponding predictions that was made from a single larger model. I think it was a wide resonant 18, so 4 times as many parameters. And what we find is that there's actually a remarkable correspondence between the predictions that are being made. So this ensemble versus this one single large model, they're not just getting the same test accuracy, they're also basically making very, very similar predictions on a point-by-point basis. So again, really emphasizing this fact that there's not much of a difference from a functional perspective between one overparameterized ensemble versus, ensemble of overparameterized models versus a single very large overparameterized model. And a question I get asked a lot about from people who are interested in uncertainty quantification with neural networks is, the result that I was showing on the left was a plot for data that was drawn from the CPAR-10 test data set, so data that looks very similar to what was encountered during training. What if we now consider some sort of distribution shift or outer distribution data? Would ensembling perhaps do something different in that case? Because that would kind of stand to reason, right? Like if we're averaging a bunch of models now that are all training on the same training data set, but could be potentially doing different things far away from this training data set, maybe I would imagine now there would be some sort of functional difference between a single large model versus an ensemble of multiple models on data that looks nothing like what I encountered during training. And what we found was that actually really wasn't the case. We again see this remarkable degree of functional similarity, even when we're using this CPAR 10.1 data set, which is considered an outer distribution data set for models that are trained on CPAR 10. So this functional similarity has a lot of implications then for claims that people are making about ensembles in practice, and especially like ensembles of deep neural networks. 5 minutes, okay, 5 minutes, yeah. I think I can wrap up by then. There's this interesting notion of effective robustness that came out in recent literature, which is saying that the degree, especially with large neural networks, when we're thinking about the robustness properties of models, especially like robustness to say shifts in our test distribution, what we really want is we want to have, when we're trying to measure robustness, we should think about robustness relative to how good the model already is on in-distribution data. So if I were to say plot the error that I was getting on in-distribution data that was similar to what I saw during training, but still, of course, test data, versus my out-of-distribution error, so error that I see on a shifted version of the data set. If I plot individual models on based off of their in-distribution and out-of-distribution error, and I plot a trend line between them, when I think about a model being effectively robust, so a model providing more robustness than what I would expect to obtain, I want to see models that fall off of this trend line, where the outer distribution, like the improvement in accuracy that I see away from my training data set is meaningfully different than just what I would expect if I had just used a better model in the first place. And so what we find is that in the case of ensembles, again, because of this functional similarity that I'm describing, we're not really getting any effective robustness. So when people talk about ensembles of neural networks, when people are using ensembles of neural networks, any safety critical applications, because they say that ensembles are providing additional robustness over what I could obtain from a single neural network, that's not quite true. It is true that if I were to consider, say, like one resonant 18 versus an ensemble of 5 resonant 18s, I'm going to get increased robustness with that ensemble than with that one small single model. But that's, again, because that can be entirely explained away just by the fact that the ensemble is getting better accuracy even on in-distribution data. And so if I were to instead make a comparison between this ensemble of smaller models versus one much larger model, then basically what I would no longer see any effective robustness because both those essentially like all of the increase in robustness that I saw is just due to the fact that the this ensemble is better. It's just a better model all around. It is going to be functionally similar to a much larger neural network that's capable of obtaining the same accuracy and distribution. I'll probably end here after this note. This result takes a little time to unpack, so I'm happy to talk about it a little bit more offline if you want to stick around. But one of the more interesting results that we had was relating this to uncertainty quantification. People use ensembles of neural networks a lot as a way of quantifying uncertainty in deep learning applications. So again, sort of looking at how different are these ensemble predictions, or how different are the predictions from the members of ensembles to one another. If we're seeing a lot of differences, that should be a notion that should be really uncertain about whatever the ensemble prediction is. And there's a lot of appeals to Bayesian inference when people are making these claims of using ensemble variance as a notion of uncertainty. But now we can actually characterize with these results a little bit better what actually is happening with the ensemble variance. So going back to this sort of decomposition, at least in the case of the squared loss, we can always characterize that variance is exactly equal to the difference between the error that I expect from a single predictor versus the error I expect from my ensemble. So predictive variance, we know amongst our ensemble members, is one way of characterizing it is the expected improvement that I would get by forming an ensemble in the first place. But now that we have characterized this functional similarity between ensembles of smaller, still overparameterized models versus a single larger overparameterized model, we also now can say that the expected improvement that we get through ensembling is also the same improvement that we would expect if we were to have just used a single larger model in the first place. So tying these 2 points together, predictive variance, which again people are using as this notion of uncertainty, all that is telling us is that that is basically quantifying the expected change in prediction that we were to get if we were to just increase the capacity of our model, if we were to just use a larger model in the first place. And there's reasons, I'm not arguing that this is necessarily a bad notion of uncertainty, but it's definitely not a standard notion of uncertainty. It doesn't correspond to like any frequent distribution notions of uncertainty that we use in practice. And in a couple preliminary experiments, we showed that this ensemble variance, like if we really get into it and we really dissect it, it's actually not providing any meaningful signal that could be used for like selective classification or decision-making purposes. So I think I will be ending on time. The main takeaways from this talk is, I guess, kind of the technical takeaways is both from this like empirical evidence on actual ensembles of deep neural networks, but also some from this theoretical evidence analyzing ensembles of random feature regressors. Overparameterized ensembles behave like single models. We're sort of losing this distinction between an ensemble and individual models that we had, say, in the underparameterized regime. Also, ensemble variance is a very unreliable measure of uncertainty. There's not really any good way to fix this. Like, there's not going to be any recipe where we can try to inject new notions of diversity or variance into these ensemble members, because as we saw in the first part of the talk, that ends up being very counterproductive to the overall performance of the ensemble. But now zooming out a little bit more beyond just the immediate technical takeaways, I think what for me is the most important findings from all of this work is that our intuitions about classical or like ensembles, so things like random forest, things like gradient boosting, these classic techniques that I think really conjure these images in our mind of what should be happening when we combine multiple models together. They really break down in this overparameterized regime. This overparameterized regime is fundamentally different, and a lot of the intuitions that we do have about ensembles really do not apply here and can in fact be backwards. And sort of one final takeaway is that because there is at least this like functional similarity between ensembles and single very large models as overparameterized regime, I'm not saying we shouldn't be using ensembles, but we should be viewing them more as tools of convenience in this overparameterized regime. Like, this is a way of one mechanism for creating more powerful models, which might even be preferable to like training one single very large neural network, right? Like, if I have, it's much easier to say train 5 slightly smaller neural networks, each on their own individual GPUs, without having to make any sort of communication amongst them during the training procedure, than training one single large neural network that needs to be distributed across 5 GPUs. There's advantages to ensembling, but not necessarily functional advantages. They're just simply a tool of convenience. And with that, I would like to thank a host of collaborators who helped to make this work possible. CAIDA and Kelly are people from my postdoc lab who are now postdocs at Stanford themselves. Nicholas Stern was an amazing intern I had over the summer who helped me get the theoretical results finally out the door. So thank you very much.
Very rigorous questioning during the talk, but if anyone has any more questions, there is some time for that now.
So the n equals p threshold is really nice in the synthetic
yeah.
But in real data, with the unidentifiable model, it's a bit more complicated. You have like practical recommendation to detect which side of the path?
I would say that probably assume you're on the overparameterized end of things if you're using a neural network in practice. I feel like there are all these formula that people come out with for like very specific architectures of like, if you have this many parameters, like there does exist some neural network that is capable of exactly producing your training data set. And it's like not that many. It ends up usually being like the parameter, like usually number of parameters being greater than number of data points is usually a pretty good count for even in the good neural networks with non-identifiability. Yeah.
Other questions?
I was still hoping for the easy fix at the end for estimating uncertainty. I'm still waiting.
No, yeah,
How hard could it be?
yeah, it's a white whale of mine.
Okay.
Yeah.
I was going to ask maybe one quick one before we end. Like, I think I'll do the last part.
Yeah. Oh, I think there was a.
Oh, was there a hand? Oh, let someone else have a question then. Yeah.
Or we can just read the question like if it's in chat or. Oh, okay. You can ask them too.
Yeah, we'll wait, please.
And it's gone, so okay.
All right, go for it.
Okay, so in the beginning of slides, you were showing all of this are up.
Yeah.
That's why it's interesting to sample method.
Yeah.
They're just saying that basically what they've done is basically increasing the model capacity.
Yeah, or rather like they're using, so I think that like this MOPA work, like I think that they were using like they were trying to use the variance of the ensembles as a notion of uncertainty that could then be used in like an exploration exploitation trade-off in reinforcement learning. And it's not quantifying a notion of uncertainty, right? There's not necessarily a way you can get around. I still think like having an ensemble is kind of useful there to get this notion of uncertainty. But what again that notion of uncertainty is capturing is like or at least like from my understanding, is just what is the difference between in prediction that I would expect if I were to have used a smaller model versus a larger model. And is that a useful notion of uncertainty? I don't know. I actually have a summer student of mine was actually investigating this with neural networks to see if like that actually was a useful notion of uncertainty. And actually just bypassing the ensemble altogether, just saying like, well, what if we had a small model and a big model, and like let's see what we can do with those for getting uncertainty. But so yeah, but like I think that there's often these claims that like in the MoPo paper too, there's these like not like Bayesian inference, epistemic versus aleatoric uncertainty. And it's like, no, this is all like, if we actually get down to it, like this signal isn't necessarily capturing like irreducible versus reducible uncertainty.
I think I'll cut
Oh,
off.
sorry, we had
Chat question.
One quick one, super
Okay.
quick.
Thanks for the interesting talk. I was wondering how we can find a single model of greater complexity that can outperform ensembles. Have you tried to quantify the point at which finding an adequate single model is less effective than just using the ensemble of lower complexity models?
Yeah, with a really quick answer to that, what we did in practice was we basically just matched models based off of their performance. Like, so when we were like looking at the kind of equivalence between two models with the functional equivalence, we took models that were getting roughly the same average error. In practice, we found that like roughly those had similar parameter counts. So like the total number of parameters in the ensemble generally matched the total number of parameters in the large single model. I think that like there starts to be some fluctuation after a certain point where that kind of rough rule of thumb didn't really apply. But there are some other papers that I know that we reference in our papers that investigate that question more.
Let's all thank Geoff one more time. Thanks for coming.